So, hello everyone. I hope you can hear me. Welcome to today's webinar on combining dynamic testing and static analysis for ISO 26262 development. This webinar is jointly hosted by Absint and Vector. Our guest speaker today is Daniel Kästner, CTO at Absint, supported by my colleague Mr. Mohamad Ballouk, Field Application Engineer at Vector Informatik. And last but not least, my name is Winfried Schröder. I am Business Development Manager for the VectorCast product family and responsible for today's moderation. Let us have a short look at our agenda for today's webinar. First, I'm going to give you a brief overview of Vector and VectorCast. Afterwards, Daniel will give a presentation and a demo on combining dynamic testing and static analysis for ISO 26262 development. Mohamad will then show you how our automatic test tools can support you in the dynamic testing of safety-critical software for the ISO 26262. And at the end of this webinar, we will answer your questions. Please use the Q&A window and address your questions to all panelists to make sure your questions get answered. So, I like to start with a few facts about Vector. We have subsidiaries in 13 countries and more than 3,000 employees which support more than 7,500 customers worldwide. Vector has several product lines, but we will focus on the VectorCast product family today. Look at the history of VectorCast, we can see that the first version of VectorCast was launched already in 1992, shown here in red. That means that we are facing a very major product. It was initially developed to automatically determine code coverage for safety-critical embedded software in the aerospace industry. In the following years, it was extended by a unit test tool. The VectorCast family of tools supports the creation and management of test cases to prove that the low-level software requirements have been tested. The first version of VectorCast supported Ada, but as the years go by, VectorCast also supported other programming languages such as C or C++. The actual version of VectorCast 2020 also supports C++ 17. In the recent years, VectorCast has established itself in many other industries than aerospace. The reason for these are the standards and obligations of the functional safety, which have found their way into all industries today. Since VectorCast has been used from the very beginning for testing safety-critical embedded systems with the highest criticality requirements, it is also perfectly qualified for use in other industries like automotive, medical, industrial, railway, and others. As you see on the right side of the slide, you will find the VectorCast products at the bottom and right side of the traditional V model, where all these tests take place. VectorCast is a test solution for all test phases, from low-level software testing to full system testing. Tests can be performed natively on a PC, but also on a simulator or the real target hardware. On the left side of the slide, you can see that VectorCast integrates with many other tools you may already have in your development environment, and that it supports almost any embedded compiler. The testing process varies from organization to organization, independent of whether the products are used in safety-critical areas or not. I think it's everybody clear that only well-tested products are of good quality and can be successfully established on the market. It's therefore important to know what the testing process currently looks like and how it could be improved. VectorCast reduces the time needed for testing through tool-supported test creation and wide-ranging automation. It increases the test frequency and enables every developer to check his code changes immediately. VectorCast moves all these controls to the right. So this was my short overview of VectorCast. We'll now learn more about combining dynamic testing and static analysis for ISO 26262 development in the following presentation by Daniel Kästner.
Thank you, Winnie, and welcome everybody from my side. I'm Daniel Kästner from Absint, and I'm going to give an overview of ISO 26262 requirements, which can be addressed by static analysis and a combination of static analysis and dynamic testing. So in my presentation, I will focus on the static analysis part, also give some tool demos, and Mohamad later will show how the testing works and also give an example of an integration of static analysis into testing in VectorCast. All right, so first let me briefly give an overview of Absint. So Absint is a tool provider. We are providing development tools for embedded systems with a clear focus on tools for validation or verification and also certification of safety critical software. And more also security relevant software, because cybersecurity requirements in safety critical systems are also increasing. Absint is a bit more than 20 years old. We are a spin-off company from the Programming Languages and Compiler Construction Group in Saarland University. The company is still in private property. We have more than 40 employees, and the customers come from more than 40 countries all over the world. Our industries are all industries which are somehow related to safety critical requirements. So this is, of course, aerospace, automotive, railway, energy, including nuclear energy or wind energy, and medical devices. So anything which is safety and increasingly also security requirements is among our customer base. All right, so this is an overview of our key products. The first three products aim at real-time systems. So their goal is to provide insight about the timing behavior of embedded software. The first tool, called AIT Worst Case Execution Time Analyzer, gives guaranteed upper bounds on the worst case execution time of tasks in real-time systems, which means that you actually have a guarantee that a certain task will always finish before its deadline. The timing profiler is a static analyzer which aims at early design phases and to provide an early feedback about the potential worst case. So for example, when you do model-based development, just by pressing a mouse click, you get an impression of what the current worst case execution time of your model would be. Then the third tool is called Timeweaver. This is an analyzer which aims at high-end multi-core processors where there is no timing predictability anymore. So AIT expects timing predictable processors to give guarantees, and in some high-end multi-core systems this is no longer possible because you have interferences or interactions between the different cores. So like quite a couple of PowerPC or ARM high-performance multi-cores. So in this case, the solution of Timeweaver is to provide a hybrid analysis, which means we combine real-time instruction level tracing without interference. So that means without instrumentation, no changes of the code, with a static analysis to compute the worst case path through the observed timestamps. All right, the next tool in the line is Stack Analyzer. Here we are computing safe upper bounds on the worst case stack usage of tasks, which means that you can prove that there will be no stack overflows when executing the software. All four of these analyzers work at the binary code. So this means that, well, this is static analysis tools, but they don't read the source code. They read the executable file and perform the analysis on the instructions of the target processor. Then another of our tools is called ComCert. This is formally and actually the formally verified optimizing C compiler, which means that here you have a mathematically rigorous proof that the compiler will not generate wrong code. The last tools here, the two last tools are Astrée. This is again a static analyzer working at the C code level now, which detects all possible runtime error, data races, deadlocks, and some other critical programming defects. Rule checker also works at the C or C++ level and checks coding guidelines like MISRA, CERT, and so on. And if you're using Astrée, rule checker is always included in Astrée. So this was an overview of our key products. Now let me briefly focus on functional safety. Well, if you look at any of the current safety norms which are around for avionics, ISO 26262 automotive, of course, railway, general electronic systems, they all require to demonstrate the functional safety of the system, including the software, of course. And this, first of all, means to demonstrate the functional correctness of the software. Well, the software has to be developed according to certain well-defined criteria, the functional requirements to the software. And if you want to show that they are satisfied, the primary technique to do this is automatic or model-based testing. So that's clear and an established technique. Then, in addition, all these standards also require to take some non-functional or quality requirements into account, which are important for safety. This again comes in all these safety norms. And well, what's it about? So for example, it says the software should not crash because of runtime errors, like division by zero, buffer overflows, error index out of bounds accesses, and so on. Resource bounds have to be respected. In real-time systems, the reactions have to occur in time. And of course, the system should not crash with the stack overflow. Then the next bullet item is concerned with multi-threaded execution. So what you do not want there is to have one thread destroy data of another thread. So if you look at different norms, you have different terminology. Sometimes this is called robustness, freedom of interference, corruption of content, incorrect synchronization, and so on. All of these are critical defects which can cause the system to stop working, to crash, or maybe behave erratically. The trouble is that it's very hard to do to try to show this by tests and measurements, because in contrast to here, it's not possible to put in focused test cases. You cannot provide a test case, please trigger the maximal stack usage. You don't really know when that happens. So that means the test end criteria are unclear. And in order to be on the safe side, you would need full coverage, which means full data and control coverage, which is certainly not possible on any realistic software. And it turns out that the technique, which is very well suited to deal with this, is static analysis. And if you use the formal method for static analysis, called abstract interpretation, you can even show that these kinds of defects will never appear in the software under analysis. So what's also important is that some of these defects are certainly safety relevant, and at the same time they are also security relevant. So that's important to keep in mind, because it means that managing these kinds of defects is not only good for safety, it's also good for security. All right, so a bit more concretely, the concrete static analysis activities which can be linked to this is checking of coding guidelines, computation of code metrics, runtime error analysis or data and control flow analysis, worst case execution time analysis, stack usage analysis. So you find all of the requirements for all of these in all of these standards. And that's also what I want to focus on in the following. Of course, with a concrete example of the ISO 26262. First, a word about static analysis before. Well, static analysis is just a technique which computes some results about the program without actually executing it. Okay? And then, depending on the depth of the analysis, you can distinguish several variants of static analysis. You can do a static analysis purely on the syntax. Maybe, of course, you know MISRA C, C++, and many of those rules have been on purpose formulated just on the syntax, which makes them easily checkable. But then, if you want to answer the question, is there an error in the program or at a particular program point? At this point, you have to go into semantics. You have to understand what the program is doing. And unfortunately, this is undecidable, which means that it's not possible for a tool to compute a correct, precise yes-no answer for every case. This means that if you run a tool on this question, what will happen is that you could get a false positive. The tool says wrongly, well, here is a defect, but actually the code is fine. Or even worse, that the tool says, well, there's nothing wrong here, but you do have a defect there. So that's what can happen. It's a bit illustrated in here. So let's say the program behaviors which can happen is this circle here, and then some defects really can happen, and some defects cannot happen. They are outside of the program behavior. Well, then you can group the tools which are working on the semantic in two categories. The first one, called bug finders, bug hunters, they can have false positives and false negatives. So this is a bit shown here. So which means they report something, it may be true, maybe not true, and they might miss some defects. The advantage of sound tools, which are based on this abstract interpretation method, is that in this case, there will be no false negatives, and this can be mathematically proven, which means that false positives can still happen, but it's not possible anymore to have undetected defects. This is illustrated here on a simple case. Let's say we want to look for division by 0. If you have this, a by 0, trivial, you can detect this syntactically. It's more difficult when you see a by b, because then you have to reason about the semantics. Can b be 0 at this point of the program? And when you have a semantic analyzer and it reports an alarm on a by b, it always means division by 0 might happen there, or not. If there is no alarm on a by b, then it gets interesting, because if you have an unsound analyzer, it still means that you could have a division by 0 there, which the tool just didn't detect. If you have a sound analyzer, it's proof that b can never be 0 at this point. So that's a much stronger property. Briefly, one slide about abstract interpretation. I mentioned that this is a formal method for static program analysis, and the benefit of this is that it really supports correctness proofs. It's an important goal of any kind of static analysis to be efficient, to scale to real-life applications, which, as of today, consist of several millions of lines of code. The tool must be able to deal with this. And this is only works if the tool does some abstractions, some simplifications. And when doing some abstractions, of course, the danger is that there is something going wrong, that you just don't simplify things, you are missing things. And doing this in a mathematically rigorous way gives you the tool to prove that nothing can go wrong, in the sense that nothing in your abstractions can ever miss true cases. So when you do this for a static analyzer, do the corresponding proofs, then you know that you're on the safe side. So yes, you might lose some precision, but you will not miss any defect. For timing or state usage analysis, it means, well, you will never underestimate the true worst case. And let's say for runtime error analysis, it means that the tool will never fail to miss a true defect in the code. Now, ISO 26262. If you look at the norm, so I'm mostly focusing on the on part 6 about software, and then in the first part of the document, it's about general fundamental topics, where the development process is illustrated. And of course, the development process is based on the V model. And when we are looking for verification activities, they are linked to the right-hand side of the V. And in the new version of the ISO 26262, you will see that here you have unit verification, software unit verification, integration verification, which is clearly defined to include both static analysis and testing, and maybe some other techniques as well. And then in the end, you have high-level validation testing in the end. So it's clear that verification activities are necessary in a well-structured development process. Then, if you read a bit further, also still in the general fundamental topics, you will see that, well, it's just an example, but it's mentioned that nowadays you should have a continuous integration based on an automatic build system, which builds the code, but also runs static analysis, also does the testing in an automatic way, and ideally in an integrated way. So you can capture everything automatically, everything linked together. That's one first important message. Now, still in the area of fundamental topics, if you want to program a system, you have to think about a programming language. What's the good programming language to do this? And you have to select an appropriate programming language and think whether you should apply some modeling and coding guidelines, if it's not perfectly suited, to make it suited for the application. So that's something you definitely have to consider. providing adequate modeling and coding guidelines for the language you're using, like enforcing low complexity, forbidding certain dangerous language constructs, try to achieve strong typing. And another goal you see here is deal with unhandled runtime errors. Okay, so it's pretty clear what you can do here, what you must do here, and where static analysis can contribute, code guideline checking, and runtime error analysis or data and control flow analysis. So this is the topics to be covered by modeling and coding guidelines. And of course, doing this has its purpose. One purpose is to make sure or to reduce the danger of code defects. Another one is to provide adequate principles for designing the software. That's also mentioned in the ISO 26262 in table 6. This is now in the software architectural design area. Like, for example, having no dynamic memory allocation, variables should be initialized, and so on. No hidden data and control flow. That's all requirements which can be linked to coding standards like MISRA C. And as you can see in both tables here, they have very high recommendation levels. So most of them are highly recommended. Now, software architectural design, if you look here, you find some definitions like static design aspects, cover data types, global variables, and some more. Dynamic aspects cover the functional sequencing of events, the functional dependence of events, of behavior, the logical sequence, then also control and data flow and temporal constraints. That also means that if you apply static analysis, it's actually a static analysis of dynamic program behaviors, okay? And you can do this. Well, principles for software architectural design. So here you see requirements like restricted size and complexity of software components. Here you're in the area of code metrics. Strong cohesion within each software component or loose coupling between software components. Here you are in data and control flow analysis and at the same time runtime error analysis because you can leverage the same activity for both of them. Appropriate spatial location, spatial isolation of software components. This is runtime error analysis. Appropriate management of shared resources. Then again, you're in runtime errors in also in state usage analysis. And then you have the temporal constraints, which means then you're in the area of timing. Okay, methods. So here you can see methods for the verification of software architectural design. And of course, you see control data flow analysis, maybe also formal verification, and also scheduling analysis involved in this. Then in the also software architectural design, resource usage is definitely a topic. There is a clear requirement. An upper estimation has to be provided, shall be made, for execution time and storage space, including stack usage. So yes, worst case execution time analysis, among others, stack usage analysis is definitely needed. Moving on to software unit design and implementation. So here, so I'll just illustrate some of the keywords. In the recording of the talk, of course, you can read the entire text, but I just wanted to highlight some important aspects here. You see consistency of interfaces, consistency of data, data flow, control flow, simplicity, readability, comprehensibility, robustness. That's all requirements here. Robustness includes execution errors, division by zeros, data and control flow errors. Verifiability, another requirement. So here you clearly see requirements for code guideline checking, for computing and applying code metrics, and to do runtime error analysis and data and control flow analysis. Methods to do this? Well, static analysis. That's this red box you see here. Control flow analysis, data flow analysis, it's static analysis. Well, static analysis, of course, is mentioned as well. And you also see abstract interpretation mentioned here. And of course, ISO 26262 also requires testing as a method of verification. You'll find this in here in this table as well. Then, same thing happens for software integration and verification. So it's more or less the same than shown on the previous slide. So all the design requirements have to be met. Hardware-software interface specification has to be met, which includes coping with the available resources. And there should be no inaccessible software. The software should be robust, and yeah, again, you should have sufficient resources, which means at this stage you need all activities I've mentioned before. And the methods, no big surprise. Again, you find static analysis, control and data flow analysis, of course, as one aspect of static analysis, abstract interpretation as a subversion of static analysis, and you will find the testing again. Okay, one aspect which is also carried throughout the norm, and you will see linked to different places in the requirements, is freedom of interference in general. So for example, this appears under the software safety requirements. And in general, freedom of interference has many aspects. It has aspects in mixed criticality softwares, interactions between software components. Then, of course, there is the classical interference in timing and execution. So that includes deadlocks, execution time problems, incorrect synchronization, and you have spatial interference. Sorry about that. Spatial interference like corruption of content, in particular due to data races, stack overflow, underflow, and cross-software element accesses. So that's again something you can discharge by runtime error analysis or data and control flow analysis. And you also have to look into worst-case execution time and stack usage analysis. Okay, now in the following I'll describe each of these activities a bit more. And so for example, for coding guideline checking, there are many tools on the market. I will focus on the Absint tool, of course, which in this case is called Rule Checker. So Rule Checker is a static analysis tool which checks for compliance with coding guidelines. And these days there is a big set of coding guidelines which are commonly accepted and which contribute to safety or security critical development, like MISRA C, C++, Adaptive AutoSAR, C++, Common Weakness Enumeration, CERT C, ISO C Secure, and more. So these standard rules checks are covered, and also code metrics are computed, and it's possible to check for violation of these code metrics. Now, very briefly, I want to give a demonstration of how this works. So I have a prepared project. So this is a small toy project. I run the rule checking analysis. Rule checker runs, and then I can see my results here. So for example, I have an overview of the MISRA 2012 rules I've checked here in this example run, and I can look at my findings, can see the different rules which have been violated, and can focus on some of the selected rules, like just picking out an arbitrary one. Like in this case, here each switch statement shall contain a default label. Well, this is a rule which is certainly not satisfied in this switch statement here. So you can see we report a violation here. You get the information precisely where on the element where the rule violation occurs. You see the rule which is violated is MISRA rule 16.4. And well, after inspecting this, you can say, okay, this is a justified defect, and somebody please should add the default clause. So that's one way to move through this. You can see in the code that there are certain other places, code places highlighted here. Those are other places where rule violations are reported. So if I click on the triangle, I see this alarm here. So in that case, let me see. Yes, in that case, you would require having the then part of the if statement in parentheses, and the else part as well. Okay, then moving on. So we have seen the overview by rule, how many rules have been violated. Then if you have commented some findings, then you see what the review status is. Here you have the per file overview, in which file you have the most rule violations, for example. And you see the overview of the code metrics, which includes the usual suspects like cyclomatic complexity. All right, so let's move on from code guideline checking to the deep semantical analysis, targeting runtime errors. So here our tool to do this is called Astrée, which is a sound abstract interpretation-based tool, which means that it will detect all runtime errors, and it will be precise so the false alarm rate is low. Runtime error here now means defects due to undefined or unspecified behaviors of the programming language. If you look at the C standard, then you will find Annex J, which lists all the undefined, unspecified behaviors of the language, and some of them can cause serious defects. Usual suspects are those: array index out of bounds, division by zero, all kinds of invalid pointer dereferences, null, dangling, pointer accesses, buffer overflows, and so on. Then there are also concurrency defects, data races, which are reported, deadlocks, lock-unlock problems, and there are some analyses targeted for cybersecurity applications, like taint analysis. You can track the flow of confidential or critical data, or in some cases also specific vulnerabilities which are reported by the tool. All right, so let me briefly show a demo of how this works. So actually, that was the wrong tool. Again, another prepared project. I just kick off the analysis. It looks a bit similar to the rule checker we have seen before. And I'm trying to make this go away again. Okay, and so here you see the top level results. I have 9 places with runtime errors, 3 of which will definitely happen in some context. Then I can drill down to the defects which are reported. So here in this case, I see invalid usage of pointers and arrays. Let's look into it. Oh, array index out of bounds access. I can click on the alarm. And then on the left-hand side, I see the pre-processed code. Here I see the original source code. And I see here, well, yes, index 10 is reported to happen by the tool. And we can see, yes, there is a loop which starts at 0, iterates including 10 on an array which only has 10 elements. So that's too much. And yes, indeed, we have an array index out of bounds, which is guaranteed to happen. So you can see that here there are different colors in the code. The most critical defects are deep red. Then here in this case, we have, for example, an uninitialized variable access, which is also reported. And the blue color means rule violations, because the rule checking is also part of Astrée. Okay, so here it's a bit similar to rule checker again. We have the overview of finding categories, the overview per file. We of course have the rule violations overview. And now Astrée also reports unreachable codes. You see the overview here. And you also see the code metrics. Okay, and then you also see these tabs here, data and control flow. Before going down into this, I will switch to the next slide. Which is this one. So data and control flow analysis basically means, well, control flow analysis shows which functions can call which other functions in the code. A code graph can be provided, and you can link function calls to threads or cores on which they are happening. Data flow analysis means you have a list of global or static variables with the interactions, who is writing on them in terms of locations, statements, functions, processes, and what the access properties are, whether it's a thread local access, a shared access, or whether you even have a data race on it. So those are the elements of a data and control coupling analysis you would need for aerospace, or interference analysis. Part of interference analysis you have to do for all safety norms. And then the important contribution of soundness here, if you have a sound analyzer, this means that no data and control flow is missed. And if you would not have a sound analyzer, it would always mean that there is some potential data flow, some potential control flow you are actually missing, possibly. Okay, so let's have a look at how this looks in the tool. So here I switch to the third project. So in this case, I have set up a simple AutoSAR system with an RXML file as a starting point. I kick off the analysis, and again, I will see some notifications about runtime errors, and in this case, also data races. And here I can investigate the data flow and the control flow. So for example, let's look at the data flow. Then I see all here in this view, I see all the variables, whether they are effectively shared between different processes, or whether there is even a data race on it. And I see the information, process local, global. I see the number of reads and writes to it. And when I click on it, I see which process and which function in which application or which core is actually accessing this variable. And if I like, I can also browse through the different accesses. So that's a way to investigate the data flow of the software. The control flow overview is pretty straightforward. You see which function calls which other function in which process, in which application, on which core. And of course, at a glance, you see whether you have some reentrant functions which maybe should not reentrant, and so on. So this, of course, gives valuable feedback. All right, moving on. Next is worst-case stack usage analysis. So as I've mentioned before, this is analysis which works at the executable code. So in this case, the analysis considers the individual machine instructions of the program. And then the analysis is pretty straightforward. It takes an entry point for a task or a thread, and then computes its worst-case stack usage with the visualization of the critical path. When you did this for all the tasks in the system and know how to combine them, then you know the worst-case stack usage of the system. Likewise, worst-case execution time analysis. So here again, we are starting from the executable level. And in this case, again, the analysis considers the individual instructions of the program, and it knows for each instruction how it modifies the microarchitectural state of the processor, like the caches, the pipelines, and so on. And by leveraging this information, it can compute a worst-case path with a program, which gives an upper bound of the worst-case execution time. Requirement is that the processor is timing predictable, like the case for many Power PCs, the Oryx processors or Tri-Core, and a lot of the ARM Cortexes. Okay, next in line, if you have a high-performance multi-core architecture, then often the process is not entirely timing predictable anymore. And then here, the approach TimeWeaver takes is, in this case, to have a hybrid worst-case execution time analysis, which means that we take instruction-level trace information, which, very importantly, must be non-intrusive, because any instrumentation would significantly interfere with the execution time, and you could not separate the effect of the instrumentation from the original program. Therefore, the tracing has to be non-intrusive. If we have this, we can extract timestamps from the traces and again compute statically a worst-case path through the program, combining these trace informations, which gives an upper bound again on the observed timing. So this is also available on timing predictable processors if they have the corresponding non-intrusive trace interface, like it's the case for the Oryx. So last demo here. So in this case, our binary analyzers are all integrated into one user interface, which means if, like in this case, I have the Oryx processor, you want to execute a stack usage analysis and a worst-case execution time analysis, you can do this in one go. And I will just do this. I kick off the analysis, and then we can see, okay, I have a static analysis. It reads the executable file of the I want to analyze. So I should see this here under file. Yes, so this is in this case an ELF file. I'm analyzing. I do not execute it. I just have the static analysis running on it. And I see the information for all the tasks I have specified. So here my first task takes 52 microseconds, the second one 186 microseconds. And the worst case stack usage here is, for example, on the 10 milliseconds task, 128 bytes on the regular stack and 320 bytes in the context safe area. Then I can also, apart from having these figures, I can drill down and look at the control flow graph. So here I can see, okay, I run into the worst case stack usage if I call the try function from here, procedure 0 from there, procedure 1 from here, and I end up at my worst case stack usage here in procedure 7. And here I can see that, well, actually this is the level the analysis works on. It looks at the individual instructions of the program. And here at this point, I reach my worst case stack usage. For timing, it's very similar. So here, let's also look at the control flow, at the call graph. So in this case, red edges mean that they're actually on the critical path, the worst case timing path of the software, because in this case, everything is executed after one another. And so here I see the top level overview. Worst case execution time is 134 microseconds. I see the number of cache hits and cache misses I see in the worst case execution scenario here. And for example, at a glance, I would see that this program almost spends half of the execution time inside the string copy function. All right, so this was a quick overview of running some binary level analysis, which already brings me to the conclusion. So If you have a safety critical system, then it's clear that you have to reason about the occurrence of safety and security hazards. And if you want to do this, then static analysis plays a very crucial role. So first of all, it's recommended by all safety norms, and it can achieve a lot of different verification goals. It can check compliance to coding guidelines, compute code metrics, do resource analysis like worst case stack usage, worst case execution time. You can deal with runtime errors. You can prove the absence of runtime errors like division by zero, buffer overflows, concurrency defects, data races, deadlocks, and so on. You can also do a sound data and control coupling analysis or interference analysis. And in a sense, what this gives you, if you think, for example, also in the area of highly automatic driving, this provides false avoidance because you can show that certain defects will not happen. And of course, static analysis can be easily automated and fully integrated in the development process. And this is something which Mohamad will show also in the next part of the presentation. So then I'm through with my parts of the presentation, and I hand over to Mo.
So yes, hello everyone. Just let me share my screen. Hope everyone can see it. So hello everybody. Thank you, Daniel, for this great presentation. My name is Mohamad Ballouk. I am Field Application Engineer by Vector Informatik, and I will show you now the other part. Well, basically the part where you do the dynamic testing. And just like Daniel already mentioned, you need to qualify. You need when you write some code that will be used in some critical areas or fields, then you need to make sure that your code does meet the requirements by the safety relevant functions of your system. So basically, I have here VectorCast, and here we are going to do some dynamic testing. I will show you how this works. I already started a project, so basically you can see I have my, let's say, a solution which contains a lot of projects. So we can do unit testing in VectorCast. You can do integration tests. So basically testing some submodules when more than one file need to be tested together, or a small module need to be tested together, up to the complete system test. So basically you have your system done, and then you want to test the complete system together, and this can be all automated and done and realized in VectorCast. Good. So talking about ISO 26262, so basically VectorCast does support several industry modes. You can see we do have here a small overview about them. Just like I said, when you are writing code for some fields, then you need to meet the requirements. And speaking about ISO 26262, there's a lot of safety levels you need to meet. And I will give you a small example about it. So basically, we are doing code coverage and unit testing today. I'm going to start by a small unit test. And when I talk about unit, then I mean a file, a C file. And I'm going to start with a very basic C file. As the name might already see, or as you might see, it's called math, and it has some functions. And for each of these functions, you can write a test. I started writing a test for the add function. As you see, I have here the input and the input values of the function and the expected value. We have a test editor where you need to fill in your input data, give the expected value, run these tests, and see the result. So basically, if I run this test, I have a match because the result does match what the function gives back. Good. So to clear it out, so you see here, I have my environment. We will set an environment in 1 minute. I'll show you how this works in VectorCast, how you can set it easily. But basically, you see that here I'm covering, or I'm calculating the coverage for this unit test based on the ISO 26262 and at the unit level ASIL-A. And basically, I'm calculating the statement coverage. You see here how much I did arrived in this coverage. So I have 6 out of 8 lines covered. It's 75% of what I did already covered, and I can see these coverage in my file right here. So basically, covering does not mean directly that your code is correct, because as you see, I have here a subtract fail where I am subtracting two values, and you see 100 minus 71, it gives 29, but I'm awaiting 29.5, and this is a fail. But basically, if I go back to my coverage, then you see that this function called subtract is already being covered. So basically, it's another topic. It does not always means that coverage means you wrote correct code, but coverage means only that these lines are called in our test, and they are working. We don't have any exceptions like null pointer or something like this. So basically, if I want now to reach the 100% coverage in this file, I need to, as you can see, everything here is green. That means it's already covered. I only have this function called divide, and it's in red. That means I still need to write one more test maybe to fully cover this function. And that can be done easily by right-clicking on the function. So basically, I have here my unit that I need to test. These are the functions inside. I right-click on it and add a new test case. And you have here the input. Again, these are the parameters of the function. And now we can type in our test. And we are waiting here for 3. And if we run now our test case, you see it's a match. And if you look at the statement column, you see this small tick, and basically it means we have now 100% coverage. Good. Daniel talked about the static analysis. What we want to show in VectorCast, so VectorCast can be one place where you can write your unit test, calculate your coverage, doing your software integration tests, and plus also calling some other tools from VectorCast, like the Absint. For example, we did a small implementation for the rule checker. So basically, if I want to calculate the static or get back or checking my file called math.c, and all I need to do is going to the analyze source and activating or clicking on this option, and now this is being called. So basically what we do is calling the Absint server, sending the file, sending the configuration for what we want to test, and here we see the results. So basically what Daniel already showed you in the tools, all these results are being also displayed in the source code directly. So basically, if you switch here somewhere, so you see that it's we switch to the message, and we show you exactly what the message means. Good. So basically, this is about small tests. Writing small tests. I'm going to show you now how we. So I'm going to close this environment. As I already mentioned, so we have here a solution, and it contains more than one project. So we have here our unit testing, we have the integration testing and system test. I'm going to create one more unit test, and this can be easily done by creating a new test environment. I already did all the configuration in my project, so a solution in VectorCast. This is a solution, as I said. A solution can contain more than one compiler node, and this is good. So basically, if you are going to test your code on a machine, and later on you want to test that on your target, so basically you create one solution. You have these multiple compiler nodes, and under these compiler nodes you do your test. You can also duplicate these nodes, changing only the configuration, and to meet your next system or the system you want to run your test on, and run these tests together. There's also a good thing about it. So basically, later on, I will show you how the continuous integration would work in Jenkins. So basically, if you have one solution like this, you can just start a job on Jenkins and then see all the results of these projects. Good. I'm going to give a name to my environment. This is basically the name of the file I'm going to test. It's a unit test, so basically I want to test one file. I want to see the function inside of it. There is a lot of options that we can do, like white box testing and so on, but I'm going to leave it right now. And here you can check which file you want to test. So in my case, I want to test my manager.c. I'm going to build this environment, and you will see in a second, VectorCast is building now let's say building a framework. It's building a test driver that will be able to call these functions inside this C file. We do use your compiler settings. So basically, we use the same language you do for writing your code for your target, and we use the same options that you use in your compiler so that we make sure we build an executable that will also run on your target. So basically, we don't use a compiler ourselves, but we use your compiler to create these test driver. Good. Now we have here our manager, and it contains some of these some of functions. I did only added one file. That means everything inside this file, every function can be tested. Any calls to any function outside this file should be stopped, and that means simulated. Let's say like this. And I'm going to add a new test for this place order. There is, as you can see, we did extract your source code. We understood exactly what's inside, so we can also understand the complex structure. For example, here we have some enumerations inside of these parameter order, and you see here we also know exactly what's inside of these enumeration. It's only because we did pass your code and we solved all the includes and all the macros. If I'm going to add here a stake, going to say I'm going to order the stake and calling here writing 14, because I know that the price of a stake will be 14. If I run this, and it will give me a pass. Now I can for sure duplicate this test case. So I'm going to duplicate it now. And as you can see, we do have here subprograms. That means this function is calling something outside of this file, outside of manager. And now I can use these functions. So they are being called, but now I can tell them what I want to get back. So basically, this place order is getting everything that you ordered before and add the new orders that you had. So basically, if I say I already added for 12 euros, and I have and I'm now ordering for 14 euros. If I run this test again, it won't match, because now the sum will be 26, and I'm expecting 14. So about control flow, there was some questions. So maybe I can show you how this is happening here. So basically, we are talking about dynamic testing. And this means here in the control flow, I can check how the functions are being called. So basically, I'm doing this place order. I can tell exactly what's happening or what I'm waiting for in this control flow. So basically, I want to run the manager place order function, and in this function there will be two calls. The one is the update table record, and the other is get table record. I know it because I know my source code. And when this is done, then the control flow or my function is done. So that means I'm going out of this function. Now, if I run this function again, you see now I do have control flows. The first one does match. The second one does not match because I'm awaiting get table record before update record, and I did just a mismatch. So basically, the get table record should be before. Exactly. So now I have here these control flows. Everything you're seeing here, so basically we create a lot of reports. You have here, you can see here the test cases, you see the test reports, and this is basically a small overview. We did what we saw is writing the unit test, but we also here saw having the coverage. So basically, we have here a column for coverage. It tells us exactly which coverage type has been given or we calculated, and we can change these coverage type by going here. So basically, we are now testing for the ISO 26262, but it has a lot of levels. I can change the level right here, and you see VectorCast will instrument your code, and it adds now the other types that should be covered with these ISO security level, safety level. So basically, we have now not only the statement, but we also have the branch coverage and the MCDC. The last thing I'm going to show you, I'm sorry the time is a little bit not too much. I don't have a lot of time, but one more thing I want to show, since I now already mentioned MCDC, there is an option. So basically, when you're doing MCDC, it's not you need to check for the branches, but you also need to check for the atomized, let's say the sub conditions inside of your branches. And if I'm going to check this, so basically I want to calculate. You see here I have two functions. I want to calculate the MCDC for them. So VectorCast gives you also a small overview, a small help. It will calculate for you automatically which conditions does match, which row does match together, which pair, and there is also the opportunity, or you have also the chance to say, I want to create them, or I want VectorCast to create them automatically for me, and they are calculated or they are inserted for you. If I execute it again and go to my coverage, then you see they are all green. That means they are covered. Great. Last thing, Daniel already talked that your test should be automated, that should be run, or every time you do a change. You have this option in VectorCast. We have a Jenkins plugin, and in this Jenkins plugin, I already have this project. So basically, this what I showed you, it's also in here. And you can see now the test results, which of these tests did failed, or all the other tests, and you also have an overview about the code coverage, and you see here what has been covered, the complexity of it, and which type of these coverage has been calculated. So great. I have to give back to Winnie. I hope you enjoyed this presentation. So now we are going to switch to the question and answer session.
Yes, thank you, Mo, for this great presentation.
Good. So I'm going to.
So as Mo stated, it's already time to ask your questions. Please do not hesitate to send your questions to our discussion participants via the Q&A window. Daniel, I see that there are already some questions for you. Can you please answer them?
Yes. So actually there have been quite some questions coming in, which is a very good sign. So I'm happy to address them. So yes, a principal question. Yes. So if there will be a recording of the webinar available. And if you're interested in the slides, then we can also make the slides available to you. So that's a pretty basic question. Okay, then the next question was which code metrics are supported and whether it's possible to customize target values. So the code metrics which are reported is basically the usual suspects based on the HIS metrics. And there is also a documentation which precisely describes which coding standards have been or are being supported, and with a very precise description for each rule and how each rule has been covered. And then, for example, with the metrics, it's possible to configure threshold violations. So, for example, if you want to have at maximum a given cyclomatic complexity, then if you're exceeding this value, then you will see an alarm. And in general, quite a number of the coding rules also have a configurable part. So, like for example, which all the rules which refer somehow to coding style, like naming of syntactical elements, that of course you can provide to the analyzer. So actually that have been two questions I've been just talking about. The next question is about qualification. Yes, so as you can imagine, all the Absint tools are used in a safety critical context, which means that eventually they will have to be qualified. And with ISO 26262, these kinds of verification tools are typically very far or very late in the V model, which means that the tool impact is quite high. in that sense that tool errors would not be captured by other tools. So yes, definitely we have to be qualified. And our strategy is to support the highest ISO 26262 requirements. We are providing a qualification support kits, or qualification support kits for all of the tools actually, which include a validation suite. So you have the full specification of the functional requirement to the tool, a verification test plan, and a validation suite you can run, which demonstrate that the tool satisfies its functional behaviors in your installation of the tool where the analysis is actually done. So this is the requirements you need for ISO 26262, ASIL-D TCL 3, and of course all lower criticality levels, you can apply this as well. And in addition, we also have evidence about our development and verification processes, so we can also demonstrate development in accordance to a safety standard, which is another acceptable way for ISO 26262. Next question about the reports. Yes, so Astrée and all the other tools generate comprehensive reports about the analysis results in different forms. So typically you have HTML reports or purely textual reports, and we also provide structured XML reports which you can automatically process by other tools. And these reports are comprehensive, so they include the full information which has been computed by the analysis. So that includes data flow analysis, control flow analysis, and so on. Next question was about worst case execution time analysis and scheduling analysis. So we do not provide the scheduling analysis. We just compute the worst case execution time for the runnables in the system, and how those are combined, that's up to the scheduling analysis. So essentially the worst case execution time analysis we are doing is an input to scheduling analysis tools which are targeted at computing the critical instance and to the worst case response time analysis. All right, so questions about the license model and the license cost are best addressed if you just send me an email, and then I would be happy to answer. Yes, then the next question was about incorporating architectural designs in the control flow data flow analysis or the race conditions. So that's basically related to our reports. So we provide the comprehensive information about the control flow and data flow as it emerges from the code, and then you can easily work with the result files or the XML result files to query any particular property you want to derive from this. So this is a quite flexible approach. Okay. So let me see whether I have missed a question. Yes, the last question is about how the static analysis is performed. So Vector provides a plugin where you can automatically launch the rule checker analysis. And the advantage of doing this is that you have the same development environment where you can do the testing and also see the results of the code guideline checking. And you can also automatically extract the build information from the testing tool so that you do not have to repeat the step for the static code analysis.
Yeah, thank you, Daniel.
Yes, I think that have been all questions. So thank you for your interest. I pass on to Mo again.
So do you like the questions?
Yes, I do have some questions for sure. It says, does VectorCast do the static analysis compliant to MISRA C 2012? So basically, I think this question has been already answered by Daniel, but basically what we do have in VectorCast is dynamic testing. What we have is a plugin, so we can VectorCast has an open interface where you can program, write plugins based on Python scripts, and with these we just showed how we did an integration or implementation for the rule checker from Absint, where you can call or you can test directly your code for static analysis. So basically, this MISRA C 2012 is done in Absint. What we do in VectorCast is calling the Absint tool and checking the guidelines. Okay. So the other question related to it, in our organization, VectorCast is used for unit testing. It's a separate module for static analysis. Again, as I said, it's only you can implement. We can do support for any other for different tools. So basically, as I said, you have this interface and you can build a plugin. Good. Another question says how traceability from unit design to unit test cases can be ensured. I'm sorry, what I didn't show. So basically, I'm going to. So if I may show my screen, Winnie, bitte, please. So basically, what we have in I'm going to share my screen again. What I didn't show, basically, you have for sure there's a requirement gateway, and it's also implemented. We do have a support for different gateways in VectorCast, like DOORS or Polarion or Integrity. And in this case, you have just like, let's say if you have DOORS, you're using DOORS, then you need to fill in some of these information. I'm going to show you a small demonstration here. I'm using comma-separated value. You need to get the fields out of it. Oops, I'm sorry, this is the wrong. So basically, we need just to import these fields, and later on, you just link them to your test case. So basically, if you go to your test case, to the requirement test case, you see they are already imported. I did that before, and we have here our requirement. Then you just need to double-click. Let's say this is my requirement that is being qualified by this test case. And when you're done, then you go back to your requirement gateway and say export the result. So you export all these test case results, the test cases that are being done together with the requirement information and the result back into your requirement gateway, where you see some more information about it. Good. So I'm going to switch back and I'm going to read. I still have some more questions. So it says, I'm sorry, I'm just looking for them. Does VectorCast tool give separate report with data flow analysis and control flow? I think this is also being answered by Daniel, and you saw how we checked the control flow in VectorCast about the function calls, but this has been answered by Daniel. Let me see what to. So if it's possible to add classification, test case like requirement analysis, equivalence, partitioning, boundary values, and so on. Yes, this is all possible in VectorCast. I'm sorry, I didn't show everything. It's a lot of stuff that you can do in VectorCast, but these can be done also in VectorCast. Yes, there is one more question. If the tool provides a comparison in terms of executable time and memory occupation between three functions. So basically, we do use your tool to flash the executable that we built to flash it on the memory. So basically, we can also tell VectorCast to check or to add more memory or to allocate more memory on your target. And I think for this to be answered, there's a small or little work to be done so that you can calculate the time for this execution for the function or the memory allocated. But this is I think this is possible, so you need to add some more effort in it, and yes, it works. I think I don't see any other questions, so yes. Yeah, I think these are all the questions. I just want to say if there's the need for more, for more showing in Vectorcast, as I said, I didn't have all the time to show everything, so please just let us know and we can arrange some meeting later on or some WebEx where we have more time for it. So.
And of course, we have more webinars about Vectorcast.
Yes.
Okay, thank you, Daniel and Mo, for your great presentations.
Actually, I think there have been 2 questions coming in the meantime. I can very quickly answer.
Okay.
One is about the size of code, which can be analyzed by Astrée. So it's hard to give an average analysis time for a piece of code, how long it will take. But the biggest analysis we have done was about 100 million lines of code, and it took about 24 hours. So that means you can really analyze very big software. And so if the software is smaller, then typically it's also a lot faster. The second question was about whether static analysis can take special care of manufacturer-provided header files and libraries. Yes, of course, you can configure the analysis to take into account heterogeneous software and also apply different sets of coding rules to different kinds of software. So if you have a mix of handwritten code by yourself, automatically generated code, code from supplier, and code from manufacturer libraries, then you can all have different coding rule sets for each of them, or you can also completely deactivate rule checking for those.
Okay,
so that was the last question.
For now.
For now.
We have to come to the end of this webinar now. If you have more questions, please feel free to send them to Daniel Kästner. You see his email address on the screen, or send them to me. I will forward them. I thank all participants for their interest. I hope that you enjoyed this webinar, and we can welcome you again at any of our next webinars. Please check vector.com for future webinars, or better, register for the next newsletter in the follow-up email. Wish you all the best in your projects. Stay healthy, everyone. Goodbye.
Same from me. Bye-bye.
Bye-bye.